MIT's ultrasonic breakthrough pulls drinking water from air in minutes. MIT engineers have developed a new ultrasonic method that can rapidly extract clean water from air harvesting materials, compressing a process that normally takes hours into just minutes. The system shakes moisture loose using high-frequency vibrations rather than heat, offering a faster and more energy-efficient path toward practical atmospheric water harvesters for water-scarce regions. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. A faster way to turn humidity into drinking water. Even in very dry climates, the air carries small amounts of water vapor. Over the past decade, researchers have created special sorbent materials that act like sponges, absorbing this moisture overnight. The challenge has always been the release step. Freeing the trapped water usually requires heating the material with sunlight, which is slow and limited by weather. A single cycle can take many hours or a full day. MIT's new approach replaces heat with ultrasound, a method that frees water much quicker. Ultrasound as a water release tool. The MIT team built a compact ultrasonic device that vibrates at tens of thousands of cycles per second. When a soaked sorbent sits on this vibrating platform, the ultrasonic waves disrupt the weak bonds holding the water molecules in place. In tests, this released the captured moisture in minutes, whereas solar-driven evaporation typically takes tens of minutes to hours. Because the system doesn't use heat, it needs a small power source. The researchers propose using a compact solar cell, which could both power the device and detect when the sorbent is saturated. This would allow the device to automatically cycle through absorption and release multiple times per day. Toward practical air-to-water generators. People have been trying to tap atmospheric water for regions that lack rivers, lakes, or even seawater for desalination, says MIT mechanical engineer Svetlana Boroskina. Now we have a way to release that water rapidly and efficiently. The research published on November 18th in Nature Communications was led by graduate student Ikra Iftikhar Shuvo along with collaborators from MIT and international institutions. Rethinking the bottleneck in atmospheric water harvesting. Boroskina's team has long studied materials that interact with the environment in smart ways, including advanced sorbents for atmospheric water harvesting, AWH. These materials excel at pulling moisture from the air, but that strong affinity for water makes the release step difficult. Any material that absorbs water well holds onto it tightly. Releasing it normally requires significant energy and time. That limitation inspired Shuvo and Boroskina to explore ultrasound. Shuvo's earlier work with ultrasonic medical devices suggested that acoustic waves might speed up water release dramatically. Ultrasound as a water release tool. Ultrasound consists of high-frequency pressure waves above 20 kHz. Humans can't hear them, but molecules respond strongly to these vibrations. At the right frequency, the waves add momentum to water molecules and weaken the interactions tying them to the sorbent surface. Instead of slowly evaporating, the water droplets literally shake loose. It's like the water molecules begin dancing with the ultrasonic waves. That motion is enough to break their attachment and eject them as droplets. A purpose-built ultrasonic actuator. The researchers designed a specialized actuator consisting of a flat ceramic ring that vibrates when energized, and an outer ring lined with small nozzles for guiding the released droplets into collection containers. Samples of sorbent material were first saturated at different humidity levels and then placed on the actuator. In every test, the ultrasonic vibrations removed nearly all the trapped moisture in minutes. Efficiency and future applications. The team estimates that this ultrasonic approach is about 45 times more energy efficient than solar-based heating for water extraction. Another advantage is compatibility. The ultrasonic unit can be paired with almost any existing sorbent material. Bordeschina envisions home systems resembling window-mounted panels. A sorbent layer would gather moisture. Once saturated, the actuator would activate briefly, powered by a small solar cell, and release clean water, then immediately restart the cycle. With fast cycling, the total daily water yield increases dramatically. This could make atmospheric water harvesting a more practical option for households